Okay, so for this last mini lecture of the day, we're gonna now look at conjugate pairs and their complementary strengths. All right, and on some of my slides, I've had this conjugate thing labeled and I didn't talk about it. So we're gonna talk about it now. All right, so we remember that HNO2 is nitrous acid and it's a weak acid. So I'll just write nitrous acid, okay? And so now because this is an acid, when it reacts with water, we know that water is acting as a base, okay? So, and I'll draw out our generic form as well. We know this is HA plus H2O in equilibrium with. And so now my nitrite, in other words, anion, my A minus, it is what we call the conjugate base. Okay, so the conjugate base is the pair of the acid. All right. So then now we know that in this reaction, right, it makes H plus or H3O plus. I'll say or H plus, same thing. Okay. But so now over here, if water is the base, then that means H3O plus is the conjugate acid of the water base, right? So notice how they make this pair. The acid and the conjugate base, and the base and the conjugate acid, okay? So now similarly, if we look at a weak base reaction, now we have ammonia, which is our base. And now in this case, water is acting as an acid, all right? And so now that means our ammonium is the conjugate acid, right? Because it was the base. Now we've added a proton to it, so it becomes the conjugate acid. And that means hydroxide is our conjugate base. And if we stop and think about this for a second, we remember that H plus is acid. So when we think about what makes the reactive part of an acid, it is the H plus. So that's why it makes sense that H plus, we would call it the conjugate acid, meaning it still has acidic properties. And then similarly down here, we remember that hydroxide is what gives the chemical properties of a base. It's the hydroxide that's reactive. And so, of course, it makes sense that our hydroxide we're calling a base. Even though it's the conjugate base, it's still a base all the same, okay? And so now what that means, there are complementary strengths between acids and their conjugate bases, or bases and their conjugate acids, okay? So for example, we remember HClO4, HCl, H2SO4, HNO3. We remember all of those are strong acids. And you notice that even H3O plus is listed as a strong acid, okay? So you notice here, these are now all of their conjugate bases, right? ClO4 minus is the conjugate base of HClO4. And notice the complementary strength here. HClO4 is listed as the strongest acid, but that means the ClO4 minus is the weakest conjugate base, okay? However, if we go all the way down here now, okay, so O2 minus is listed as a strong base, and so its corresponding conjugate acid is hydroxide. I realize it doesn't make sense to think of hydroxide as a conjugate acid, but you notice that's why it's called a very weak acid. So these things are opposite, okay? And I'll pick on an example to kind of demonstrate that. Let's pick on the, well, let's see here. So I'll pick on a couple examples. So let's continue to go with the top example. So let's look at HCl, okay? So when HCl dissociates, it dissociates into H plus and Cl minus, okay? So you notice that Cl minus is listed as a very weak base. And it is. Chloride is an incredibly weak base. And so if we remember, what is a base? Well, a base is a proton acceptor, right? So that means that chloride wants to accept a proton like so. However, because chloride is a weak base, this just doesn't happen. And so that's why HCl is a really strong acid. But however, if we look at something that's kind of like in between, like let's look at the HF, okay? So we know that HF has some sort of equilibrium reaction, okay? And so we notice here that it's right in the middle. And what that means is it's not in this very weak base category. It's just in like the ordinary garden variety weak base category, okay? And so what that means, fluoride does a pretty okay job of accepting a proton from that free hydrogen. And so what that means is this backwards reaction is far more likely than the forward reaction. Okay, so that's what makes HF then a weak acid. And of course, once again, I picked this middle example just so that we can see that, if HF here is listed as like a medium, let's say, weak acid, then of course F minus is going to be like a medium weak base. But the fact that it's a medium weak base is really telling us like why it sends the reaction back this way. Okay. It also tells us why in the case of chloride, in the HCl example, why the chloride does not accept another proton, because chloride is such a weak base that this reaction goes forward to completion. Okay. And we could think of that with many other of these complementary examples. But the main thing to note is this cutoff here for the strong versus the weak, right? Somewhere around there, okay? And you can see all of these ones that we talked about up above, most of them anyway, are there. And a lot of these other weak acids, such as acetic acid, so this one's formic acid, nitrous acid, hydrofluoric acid, they're kind of in this middle category. And that's why we see them exhibit this kind of equilibrium, because both forward and reverse reactions are possible, where the reverse reaction is more likely. Okay, so hopefully that all makes good sense.